Good morning, good afternoon, or good evening to all of you, and welcome to part one of our webinar series on risk mitigation in the pharmaceutical QC laboratory. My name is Isabelle Vutrieux, and I will be your host for this three-part webinar series. It is my pleasure to introduce today's speaker, Dr. Amanda Guiraldelli from the US Farmacopea. Amanda has been with the USP since 2012, and she holds the position of Scientific Affairs Manager and Principal Scientist in the Compendial Science Group General Chapters. She also serves as Scientific Liaison for the USP Measurement and Data Quality Expert Committee, where she works to develop and revise USP standards related to analytical procedure lifecycle and validation. Amanda's full biography is available on your screen, so I invite you to read this. I also would like to invite you to enter your questions in the Q&A box on your screen. You can see on your left that you have resources available that you might be interested in. And last, I would like you to complete the survey before you leave today's webinar. And now, without further ado, I would like to welcome Amanda. She will speak to us about the harmonization of USP General Chapter 621, Chromatography. Amanda, welcome.
Yeah, good morning. Hi, everyone. Thank you so much, Isabelle, for the kind introduction and also for inviting me to speak today about the chapter of USP 621 on chromatography. As probably the most of you know, this chapter was harmonized with the European and Japanese Farmacopea. And this is the agenda for my talk. I would like to start by discussing a little bit about the harmonization process itself. And then you will see that my talk will focus on the most relevant changes that we incorporated in the chapter 621, including like definitions, also the new requirements for system suitability. And also I have some case studies to share to illustrate how we can do some adjustments in the chromatographic conditions, even when we work with a procedure that we use like gradient dilution, okay? And then my last slide is just to illustrate some of the chromatographic tools that USP has. Not quite sure if you're all familiarized with them. And some of them may really like assist us when we are, proposing the changes of columns and so on. Well, starting with the harmonization process, right? So the harmonization of the chapter 621 started back in 2010 when the Farmacopea discussion group, so the PDG group, identified this topic to be harmonized among the PDG pharmacopoeias. So the PDG is a group formed back in 1989 and is consisted of representatives from the United States Farmacopea, European, and Japanese Farmacopea. And they pretty much focus on, selected official and broad impact general chapters or CPN monographs with the goal to harmonize these standards to help eliminate or minimize the need to perform multiple tasks and also procedures and to comply with multiple acceptance criteria for the same article. Okay, and from 2010 to 2007, as you can see here, this was the time actually needed for the creation or for the final to submit the final proposal of harmonization for the chapters related to chromatography. And in 2017, USP published the chapter, the proposal in the Farmacopea Forum. And this is actually the time we have for us to go there, and this is public consultation period, right? So we can go there, read and share comments, but only in 2021, so the PDG actually signed the approval of these changes, and basically for USP at least, so the chapter 621 became official last year, December of last year. But, in this period here, we received a lot of comments, especially for a specific section called system suitability. You're going to see that we have two new requirements for system suitability. And for this reason, we decided to provide more time for the industry to do risk assessment and check, the impact of those changes. And then last year, we published a revision bulletin saying that although the chapter will become official in the USP and F, the section system suitability will be delayed. And you're going to see that this will become official now, December of this, 1st December of this year. So we still have some time, to do some risk assessment related to this section. And we also published at the beginning of this year a notice of intent to revise, because you will see that one of the changes we proposed was exactly to change the way we calculate the sign-to-noise. And I will show you more details later. But we decided actually this year, and since April of this year, the USP Chapter 6.1 already includes like the old approach for the calculation of sign-to-noise, okay? Well, basically, this slide is just to show you the other chapters. So we have the 6.1 from USP, but the European Pharmacopoeia and Japanese Pharmacopoeia chapters, they also contain these allowable changes and new system suitability requirements, okay? And what are the most important issues that these pharmacopoeias wanted to address? Right, so this is basically the need to include some additional requirements for system suitability to help users to ensure that the procedure is fit for use. Also, to include some allowable changes for some chromatographic factors. And now also you will see that we can change like the column geometries, also like, migrate from one column to the other, where we go to a column with under 2 micrometers particle. Also use, or migrate to a column that has like a superficially porous particle or fused core shell particles, right? In case the reference column uses like totally porous silica particles, or vice versa is also possible. And also help to do the scale up of procedures and migrate from platform to platform, like HPLC to UHPLC, not just for isocratic elution, but also for gradient elution. Well, with those two next slides, I would like to summarize all the relevant changes we have in the chapter. And then I have some case studies to illustrate some of them. So we're starting with the section definition, okay? So there we included the definition for dwell volume. We also included definitions, that are commonly used in size exclusion chromatography. You will see that the resolution equation was kind of changed a little bit, and this may impact on the value, on the result. So we need to do a risk assessment here to check the impact of this, and I have a few slides on this one. We also included a formula to calculate the resolution for TLC, thin layer chromatography. And I mentioned already about sign to noise is all fine. So we're still using the old approach for calculating sign to noise. And in terms of system suitability, so we included a new requirement for sensitivity check and for peak symmetry check. Okay. And then I believe this is one of the heaviest part, let's say, of the chapter 6.1, the adjustments that are now allowable, not just for, procedures, chromatographic procedures using isocratic elution, but also gradient elution. We also included some allowable changes for TLC. We included an equation to calculate injection volume, and before we didn't have one, and the section where we can do some changes when we work with gradient elution. Well, let's start with this part first. I have some case studies to share to illustrate how we can propose the migration of, LC platforms, or even like changing the LC columns I mentioned, and so on. Well, just would like to start with that. So for all those factors, actually, we can propose changes for those factors. And before the harmonization, we could do this, but only for isocratic elution, okay? Procedures with isocratic elution, and now we can do also for gradient elution, okay? And I will start with some, requirements, important requirements. So first, changes are other than those indicated in the chapter 621 require basically full validation. Okay, so we need to have this in mind. And it's also important to have in mind that multiple adjustments can also have a cumulative effect on the performance. Okay, even though you're not changing so many factors at the same time, it's important for us always to conduct risk assessment. Usually it's interesting, and we strongly recommend that the risk assessment, it shouldn't be done by just one person, right? So we should really do identify potential risks of changing those factors and how this will impact on the performance. We can talk with a group of people before we decide to go ahead and implement the change, especially because we also need to verify, probably running some experiments, additional experiments for verification, to record or to have like data to support the implementation of that change, showing that actually this won't impact significantly on the procedure performance. Okay. If the adjustments are made to a pharmacopoeia procedure, additional verification tests may be required, as I mentioned, and you're going to see that sometimes only ensuring that we meet the system suitability requirements might not be, sufficient. So we need to make this. We need to go through that and decide what is the verification protocol we need to implement these changes before we do the implementation of the change, right? Just one example, let's assume you have a quantitative procedure to quantify organic impurities, okay? And for some reason, the procedure, which is the reference procedure, does not include a sensitivity check. But we know this is pretty important. So we may want to go and, not just check the system suitability requirements, but also include new experiments that we wish to show that actually that implementation of change won't impact significantly on the performance, okay? To verify the suitability of the adjusted pharmacopoeia procedure, so we need to assess the relevant analytical performance characteristics. And when a pharmacopoeia procedure has been adjusted according to the requirements stated in 621, no further adjustments are allowed. So if you do, you need to conduct the full validation. Well, with those next two slides, I would like to compare some of the chromatographic factors that can be changed. So putting side by side, a procedure that uses isocratic elution or a gradient program. Okay, so you will see that basically for both of them, we have like the same acceptance criteria or requirements. Like we can change the column length, we can change the particle size for both of them. And you're going to see that we have, what we call as LDP ratio that we use to calculate acceptance criteria. And you're going to talk about that later. We can also change the column internal diameter of we can also change injection volume. We can change flow rate. For gradient elution, we should also add some changes to the gradient volume. So we are going to talk about strategy for doing this. Regarding stationary phase, you're going to see that this is one of the most critical, part, because sometimes we overlook this, right? So we need to ensure when we are proposing the change of columns that we are really selecting the second column or the replacement column should have like a very similar selectivity. And sometimes we just forget, to look at all the different LC columns attributes that may impact on selectivity. So we are going to talk about that later too. Porosity, as I mentioned, we can, do changes in columns that we have like a totally porous particle or a superficially porous particle, and vice versa, but we need to, have a look at the performance, if this will have a significant impact on performance. In terms of column temperature, this is a bit different for both elution types. We can allow for plus minus 10 degrees Celsius of variation for isocratic elution and 5 for gradient elution. For both of them, we can propose changes to the mobile phase composition. pH of the aqueous mobile phase, basically plus minus 0.2 units can be changed, and as expected, no changes are allowed for the detector wavelength. Well, now let's review here, the approach that we can use here to really go ahead and change like columns I mentioned when we have gradient elution, okay? And this is pretty simple as it is on the screen, okay, I swear. So where you have 3 steps. So first, you adjust the column length and then the particle size according to the LDP ratio, and I will show you how. And then as soon as you find the right dimension of columns, okay, respecting, right, the acceptance criteria we are going to be calculating. And after we ensure that the replacement column actually has a similar selectivity, we go ahead and we adjust the flow rate, okay? After we adjust the flow rate, we adjust the gradient time, okay? So let's exercise this here with a case study. So here, my case study is the following. So we have a monograph, and we wish to adopt that procedure, but we do not have the column, actually, the column used in the validation of that procedure. We do not have this in-house. So we are going to be proposing the change of that column, okay? So what we have here is the monograph. Okay, this is an example like a bacavir sulfate. So here we have the organic impurities procedure. You see that this is using liquid chromatography, and we have here the dimension of column used, and we have the type of column. So probably you know that USP has developed a classification approach for columns. This is the L classification for LC columns, right? And L1, probably you know very well, this is a C18 column. If you scroll down to the bottom of the monograph, you're going to find this database here, okay? If you click there, you're going to be directed to this site where you can include the name of the monograph. You wish to find the reference column. The reference column is the one used to validate the procedure. In this case, we are working with organic impurities, right? So we could find that the reference column is a symmetry C18 column. And this is pretty important. Why? Because we need to ensure that the column, the replacement column will have a very similar selectivity to this one. So we need to do this step. So we need to go through this step before we propose the new column, right? And on this slide, you find some attributes of columns. So we are going to be talking later about some attributes that impact greatly on selectivity, but you see some of them here. And basically, they impact like more significantly on efficiency, like column length. And we see here, some parts. So in this case, this is a column based on silica particles, and this was functionalized with C18 ligands, as you can see here. So you see that other attributes are particle size, pore size, superficial area, right? And in this bullet point, we see exactly what is stated in 611. So the particle size and or the length of the column may be modified, provided that the ratio of the L to the P remains constant in the range of minus 25% to 50%. So basically what we need to do, and I will go to the next slide to show you. So this is the dimension of column of the monograph. This is the reference column, and we need to find a replacement one. We just need to use this, this year to calculate the LDP ratio for your new column based on the LDP ratio of the reference column, right? 150 divided by 5. So this is pretty much the acceptance criteria you have to select the dimensions of the new column, okay? And before I show you how to select that, I just would like to show you that we can also change the internal diameter. And I will read that together with you because you may feel like at the end you can't change, but you can. Like in the absence of a change in particle size and or length, the internal diameter of the column may be adjusted. Okay, you may feel okay. So if I change the column length and the particle size, I can't change internal diameter, but it's not true. So you can also change that. Okay. And here what I have is a table where I just put like different particle sizes here, different column length, and then I just calculated the LDP ratio. And remember, so we calculated together the acceptance criteria based on the LDP ratio of the reference column 1. And here, highlighted in pink, you see several column dimensions that would be within that acceptance criteria, and this is what is going to guide me to select, the new column. Okay. But before we go ahead and select the new column, we need to make sure we work with a column with a very similar selectivity of the when you compare to the reference column. And this is exactly what you find in the chapter 6.1. No change is allowed in the identity of the stationary phase. And this is pretty much like, okay, if the column 1 is C18, you need to continue using a C18. If this is a PFP, you work with a PFP and so on. Okay, this is what is described there. And also, you should have in mind other physicochemical characteristics of the stationary phase, because we know they can impact on the selectivity of columns. And this is everything you have in terms of guidance in 6.1. Like, have a look at the support. Is there some kind of surface modification? And then I have on this slide exactly like an illustration to show you how huge it is, the universe of C18 columns, just to give you an idea about other attributes that usually sometimes we overlook, right? We just think about the type of ligand or something like this. But have a look at this. So we have a C18 column that may have a non-polar end cap group, and other one that may have like a polar end cap group. So we may explore, different type of intermolecular interactions with the set of compounds you have in your mixture, right? And these can lead to different selectivities. So you can have C18 columns without end caping at all. We can also have, polar group embedded in the alkyl chain. This is just to show you that there are different technology of columns, and even though you have the same, ligand, let's say, you may still have different selectivities. Okay. And this is why I created this slide here, basically summarizing some of those attributes. I would like to highlight those that may really impact on the selectivity of columns, because we need to put some thoughts on this before we go ahead and select the replacement column, right? Like usually attributes of columns that will impact on selectivity, they are more related to chemical properties. So this is easy, huh? The type of the ligand, okay, C18, C8, and so on. But what about percentage of carbon load, right? The carbon load refers to the percentage carbon content of the silica in the stationary phase. And you can have, high loading columns, you can have low loading columns, and these may really impact on selectivity, okay? The different end cap technologies, polar group, non-polar group, or embedded group in the alkyl chain, as I mentioned before, right? Some of those, that are really great technologies to help reduce, ionic interaction between like the positively charged compounds with the silicon oxides group, present in your column, in the surface of the particles, right? So we need to take this into consideration. And also, like with the polar groups, like embedded in the alkyl chain, again, exploring different kind of intermolecular interactions, right? So we are changing the selectivity of column. When we go to like, issues regarding non-specific binding, the use of hybrid silica, some columns with charge surface modification, right? So we need to take this into consideration. I also think you also need to put some thoughts around some columns that are not compatible with 100% aqueous. So can you imagine if you select a column where in your gradient program, you start with initial hold, which is like 100% of the aqueous phase, and probably the column selected for validation is compatible with that, and then you select one which is not, right? So for doing the migration of columns. So we really need to have this in mind, okay? Basically, so I believe you can see my screen now. So basically, although the USP chapter 611 is pretty simple to follow, you saw that 3 steps, right? This is not a super easy task, and we should really like use a risk-based approach to select the appropriate columns. I believe I convinced you already, right? So knowing and controlling the chromatographic selectivity in LC is really important, especially for 2 things. First, procedure development, we know this, right? Usually now we would like to select columns with different selectivities and do a screening. And at later stages of the procedure life cycle is also important, like for you to find a backup column or a replacement column, right? This is pretty important during the transfer of procedure, adoption, verification of procedures, and implementation and using of that procedure, during the routine analysis, right? And this is the reason why USP created back in the 70s, the L classification of columns, okay, to help find alternative columns or alternative equivalent columns. However, since it couldn't address some of the needs of modern liquid chromatography, USP also created the USP columns equivalency tool. And you are seeing this on the screen right now. So there are 2 approaches, the USP approach. So the one I'm showing you is the PQRA approach. Okay, this was actually developed by the Impurities Working Group of the Product Quality Research Institute Technical Committee in collaboration with Dr. Lloyd Snyder and Dolan. Probably have heard about them if you're chromatographists. So this approach is based on Snyder and Dolan hydrophobic subtraction model, okay, which helps characterize the selectivity of reversed phase LC columns. And these column selectivity assessments have been enabled by the development of what is called F factor, okay? So basically, if you assess this link here, so you can go ahead and include the reference column. Let's say you would like to adopt like some compendial procedure, but you do not have the column identified in the column database. Okay, so you include the reference column here, and then you say you want to see the similar columns because you want to replace that one without impacting significantly on performance. And what you see here, a table with several columns, and oh, I'm not so good with that. So I'm trying to draw on a row here to show you the F column, right? So I didn't include this on the slide, but if you want to take note, so basically you can select columns with F value below 3. So they are considered columns which are like equivalent. And just to illustrate that, so this is a reference column, and you have the chromatogram there, right? Now showing the product column with F equals 0.5 below 3, right? So you see that the elution order is pretty like the same, no change in selectivity, but when you go to a column with a F value above 3, you see some issues here, in terms of elution order for delayed eluting compounds and so on. So this might be an additional tool for you to use to assist and select like columns with similar selectivity. And we know that there are other tools out there, right? Well, and with this slide, I just would like to summarize what we have done so far for this case study. We understand now why we selected this dimension of column, right, based on the LDP ratio, correct? And then we need to adjust the flow rate, step 2, remember? But before we discuss about that, I just would like to show you that we can, express the efficiency, the column efficiency quantitatively by calculating the number of the theoretical plates or also the height of the theoretical plates, right? And then you are probably asking, what is a theoretical plate, right? Sometimes it's so abstract, right? So what I try to do here is I just try to draw to illustrate a column, LC column, and you see like this, it's like really like, some blue plates. I try my best, okay? So you see like several of them, right, in the column. And basically one theoretical plate is the stage that the compound you take, for basically interacting with the stationary phase and then going back to the mobile phase. And this will happen all the time till the compound can lute out of the column, okay? So the higher the number of theoretical plates, the thinner is going to be the peak, better performance, and we can also think about the height of the theoretical plate. We wish now to have like a reduced height of this, because then this will imply we have better performance. Hope this was clear. And this is me again trying to show you some fundamentals of chromatography for us to understand some issues we may face when you're, suggesting migration of column or LC platforms. Like we can also, describe the height of the theoretical plate by using the Van Dinter equation. This is describing this height based on 3 terms, A, B, C. And basically, the term A is the eddy diffusion. This will, basically show the effect of the existence of multiple paths between the particles of the stationary phase. It means like when the compounds, the molecules of the compounds are luting through the column, along the column, right? It may take different paths. And there are some factors that may, mitigate and minimize that, improving performance. Like if you work with columns with reduced particle size, okay, this will actually provide the opportunity to have like a more homogeneous packing, reducing the number of multiple paths and mitigating and reducing this term, basically. So the other one is the B term, longitudinal diffusion, which is basically the natural phenomena that the molecules will, experience so they tend to go from where they are most concentrated to where they are less concentrated. And we can mitigate this by finding the optimal flow rate, And then the last one, and I usually say this is the most critical one impacting performance, is the C term, resistance to mass transfer. And this is basically any factor that is causing some sort of delay or resistance for the compound to go from the stationary phase and go to the mobile phase, right? So this may increase this C term, and then this may, reduce the performance. So one example, like when we work with reduced particle size, okay, so we can help improve performance. We can also control like viscosity. Sometimes we do this, right? We increase the temperature, this decrease the viscosity of mobile phase, and it's easier, let's say, for the compound to diffuse from the stationary phase to the mobile phase, okay? Well, and why am I telling you this? Because we need to change flow rate when we change the columns dimension, right? And when we do this, and we do this because, the optimal linear velocity is going to be proportional to the particle size, and we change that, right? And we need to make sure that we still have, the performance we wish. Otherwise, we may have like sensitivity issues. Let's say we are again, working with an organic impurities procedure, and then you do not adjust this accordingly, and you have like a reduction of performance, and you cannot detect the impurities anymore, okay? And this is the reason why in 6101 you find an equation to calculate the new flow rate for the new column. Okay, this is based on the internal diameter of the column and the particle size. So let's exercise now this calculation, which is pretty simple. So this is the monograph. So this is the column we have. We identify this column here to be the one to be replacing the monograph column, and we just need to calculate the new flow rate going from 1 to 2 in this case. Okay. And as I mentioned before, actually, we can also change columns that, like, let's assume the first one has like the totally porous particle, totally porous silica particles, and you would like to go to one that has like a core shell particles, or even worse, you have the reference column using core shell particles, and then you do not have this in-house. So I will have like one which has like totally porous silica particles, right? So what I would like to show you here is that we need to put some thoughts on performance, right? Because this can impact on efficiency, on performance of analysis. And this is, so we can explain that by going again to the Van Dinter equation. Remember, A, B, C terms. And starting with the eddy diffusion, right? The term A, because the core shell particles, they have like a solid core, right? They are denser, they are heavier. This may, help to have a more homogeneous packing, reducing that multiple paths that the molecules of your compounds can go, helping to mitigate, or decrease or narrow the peak shape, okay, increasing performance. And also the term C, basically because we now see that there is like lower resistance for the analyte to go from the stationary phase, right, and then go to the mobile phase, especially if you compare like the same particle size, like totally porous particle size, particle and core shell particle the same size. So you may have a strategy to increase performance if you use like the superficially porous silica particles. Okay, and this is all to justify why we have this sentence in 621. For the application of particle size adjustment from totally to superficially porous particles or vice versa, we need to evaluate the performance. This is pretty much like the equation to calculate the number of theoretical plates. And remember, this is a way that we can quantitatively express the efficiency, performance, right? Well, let's exercise now the adjustments of the gradient volume. So remember the third step for us to complete the migration of the column or the LC platform. It is to adjust the gradient volume, okay? A change in column dimension impacts the gradient volume, which also impacts on selectivity. So the point here is to ensure that we have this ratio of gradient slope to column volume, okay, constant. So basically you have the gradient volume here divided by the column volume, and you used to have this constant, okay? And by deriving this, we will go and have this equation that you find in the chapter 61.1 to help you calculate the multiplier. So this is gonna be the multiplier. And you use this value here to multiply by the gradient time of procedure 1. Then you can calculate the new gradient program. So let's exercise this now with our case study. So here we have the gradient table for the monograph procedure. Okay. Everything we need to do, we just need to use this equation here, where you need to have like knowledge about the flow rate, the column length, and internal diameter of the column. And then you can calculate the multiplier, as I mentioned. Just an example, for the first step, right? We have like 20 minutes, which is the original program. and you will multiply this by the multiplier, and now you have the final time for your new procedure, okay? Well, again, I mentioned about that. So when the column dimensions are changed, we may need to change the injection volume, especially if you're going, to a column that now has sub 2 micrometers particles, right? So if we just keep the injection volume, this may overload the column. We may have really serious performance issues. So we have now in 6021 an equation to help us calculate that. Important here is to emphasize that even in the absence of the column dimension, the injection volume may be changed, okay? But we need to make sure that we still fulfill the system suitability criteria, and especially if you are, decreasing the injection volume, making sure that we have still good sensitivity. So we may need to really draft a very good verification protocol to provide evidence that this change is okay. So this is pretty easy, huh? So we just need to apply the equation. So by having the column length and the internal diameter of the column, and see here that for this new procedure, we need to work with 18 microliters, okay? Well, and now a discussion around the dwell volume. As I mentioned, USP included in 6021 now the description. So what is the concept of dwell volume? Okay. By definition, dwell volume is the volume between the mixing chamber and the column inlet, as you can see here. Okay. This is just an example. Okay. And in other words, the dwell volume is the volume required for the change in a gradient to reach the column. Okay, this factor can then impact on selectivity, sensitivity, reproducibility, and very often, sometimes we overlook, to assess the impact of this factor, and sometimes we face some issues when you're transferring the procedure, right? And guess what? The different systems with different configurations and from different vendors, they may have different dwell volumes. And often, as I mentioned, this is a factor responsible for robustness issues that we face, in the receiving unit, like in the QC lab. So when we are migrating the LC platforms, or changing column dimension and going to another system, right? So we need to make some adjustments, usually in the initial hold, in the time for the initial hold of the gradient. So let me show you an example. And you see here first that USP now has also an equation for you to calculate the new time for the initial hold. So this is the initial hold of the gradient, okay, where we keep at a certain percentage of the let's say organic solvent in this case, for reversed phase chromatography, and then the concentration of this solvent is start to change, right? So we can calculate this here by taking into consideration the flow rate and the dwell volume of the system 2 and the system 1. System 1 is the reference instrument, let's say. And I believe this example here may help. So let's assume we have the reference procedure was validated using a system with dwell volume of 2 ml. Okay, and we are going to be transferring that procedure to our system, and this has a reduced dwell volume. So we have 1 of dwell volume. Okay, so basically what is happening is, so this is the reference gradient here. Okay. And this, if you do not change anything, so this is what is going to happen. Because we have a reduced dwell volume here, you see that the time that the gradient is changing is it's not the same profile, right? And this, depending on the procedure, if you did not develop a procedure which is robust to these changes, this may impact on sensitivity and many other performance characteristics. So what we would like to do here is just to add, in this case, an increment to account for that. Okay, so if you do now the opposite, let's say that our reference instrument now has a reduced or a lower dwell volume, like 1 ml, and then we have the new system. It has like a higher dwell volume, right? Now it's the opposite, but you see that the when you have a look at the profile, right, of those two instruments here, you see that the time that the gradient is changing is different, right? And again, so in this case, what we need to do to have this profile here of the reference procedure is, in this case, to do like a deletion of an increment, let's say, and now you see that this is following exactly the procedure 1 profile. Okay, this is what is behind this. And what I'm going to show you is an example again. So we have here the isocratic hold time for the monograph procedure. You see that we have a hold of 3 minutes, correct? We need to add an increment or delete an increment depending on the dwell volume, the new dwell volume of the new system. And we can use the formula, right? So basically, the information we need to have is the dwell volume of the system 2 and the dwell volume of system 1, flow rate, and then we can calculate the increment and include it here. Okay, you will find some, calculators that are provided by some of the LC system manufacturers, right? Where it can help you greatly to do these calculations. But now it's important to mention this is also, stated in 621. Important at this point is to read this sentence exactly as it is in 621. All these changes, they are acceptable, provided that the system suitability criteria are fulfilled and the selectivity and elution order of the specified impurities to be controlled are demonstrated to be equivalent. So that is why I put some emphasis on discussing some attributes of columns that may impact on selectivity, since we may, sometimes overlook them. And then have issues like, change the column. Although you are following 621, for some reason you use a column which is not equivalent, and then you saw like some elution order, changing. So this is pretty much important for us to have in mind. And this is just to illustrate like the final of our case study, where we tested different columns that are according to all the acceptance criteria I mentioned before. You see that the system suitability requirements, they are passing, like just highlighting the most critical one, which is the worst critical pair between abacavir and transabacavir. All of them is still like above 1.5, which is the requirement, but also checking overall the selectivity. Second example is pretty quick. It's just to illustrate how we go from an HPLC platform to a UHPLC platform, applying everything we have discussed so far. So now we want to go to UHPLC, and probably you're going to be working with this, particle size. And I just illustrated here some of the columns that will be within the LDP ratio. Okay, so we can select any of them. And this is just to summarize our decision. So you're going from a column with a column diameter 3.9, going now from 2.1, and decreasing the column particle size to 2.5 micrometers. Okay? And then now it's going to be easier. Huh? I could have done this before. It would be faster. So I have just a table now with all the factors we need to change, right? Like we ensure that this new column here is within the LDP, right? Rachel is 30. Before it was 30 and is within 30. Then we go and we change the flow rate. In this case, we use the formula I showed you before. So we should work now with a flow rate of 0.7. And then we calculate the multiplier, right, to adjust the gradient time, the gradient volume. And this is 0.25. And now I have here the new gradient program, okay, going from run with 50 minutes to 12 minutes. And again, adjusting the injection volume. So we applied everything I said before, okay? Okay, well, I mentioned before that before the harmonization of 621, So we already could do some changes for isocratic elution. This is just to show you, I just would like to highlight this one here, although it's not new. When a change is made from a column with particle size above 3 micrometers going to below 3 micrometers, in isocratic separation. So we need to change flow rate, which is obvious. We discussed about that. And we should ensure that we do not have a drop in more than 20% in terms of performance. Okay. And I also would like to show you that we included first some allowable changes that can be done now for TLC. Before we didn't have that. And you also find actually some adjustments that can be done applied to procedures using gas chromatography. Some of the factors and ranges were slightly changed. So I always recommend you to go to the 6021 whenever you want to do the change. Okay. Let's go to definitions. I'm almost finalizing my talk. And some chromatographic parameters, they were changed. The definition was changed and how we calculate them. So one example is the plate number. So the plate number, this is how it was before, and now how this is now. Okay. So before we were using to calculate the plate number, we were using the peak width at its base, right? So basically, we're using this here. And now we deleted this. We can just calculate the plate number by using this value here, which is the peak width at the half height. Okay. What is the consequence of this? This may slightly change the result. Yeah. For this reason, it's important that in case we have, acceptance criteria, and we use like the old way of calculating the USP plate number. So we may need to do some risk assessment and assess the existing procedures. And the same is true for resolution, and it might be more critical than the other one, right? And the same change was applied. So before, basically, we could calculate the resolution based on the width at the baseline of the peak. And now, how this is, we use the width at the half height. And again, this may slightly change the resolution, and we know that sometimes we work so hard to have like a selective procedure, right? And sometimes we have like, so we can do better, and we have like a resolution which is very close to the specification limit. So this is pretty much important for the industry to do like a risk assessment and check if it still complies, okay? And then signal to noise, as I mentioned, I will not like spend too much time on this, but basically the first proposal was the following. So actually the old chapter considered that to calculate the signal to noise, we do like 2 multiplied by the height of the peak divided by the height of the baseline. And how do you, estimate the height of the baseline? Basically by taking a distance of 5 times the width of the at the half height of the peak. Okay. And then USP proposed it, and the other pharmacopoeias proposed it, now changing the way we estimate this by increasing the distance to 20 times. And for sure, so if there is like small peaks, there, so this might drastically decrease the signal to noise. And what happened is, do not worry about this one, because this was changed already to 5 again. So we still keep the old procedure, the old approach for that. And system suitability, the last section of my talk today. First, why are system suitability requirements important? Okay, and what are some tricky things that sometimes we always have questions, like retention time and relative retention times. They are usually provided in monographs, right? But this is just for informational purposes, okay? This is important, there are no acceptance criteria applied to relative retentions, okay? And we know that usually, so some industries, they just include like an internal requirement for this, but in terms of pharmacopoeia requirements, there is any. Okay, I just wanted to make sure this is clear. compliance with system suitability is mandatory, right? So it's required for you to go and start analyzing your samples. And what I'm going to show you here is a requirement that was already in the old 621, okay? Before the harmonization. This is to check system repeatability. And usually the way we do, we just, run some replicates, we inject the same sample several times, and then we can basically express the system repeatability by calculating the relative standard deviation. And not quite sure but 621 is telling you that when you go to a monograph, okay, and then you find a system repeatability check as part of the system suitability, and it's telling you the relative standard deviation should be 2 or less, okay? Actually, usually the monograph will not tell you how many replicates you need to inject. So you need to go to 621 to find that. Just wanted to share this again with you in case you didn't notice this. In this case, you need to inject like 5 replicates. If the monograph requirement is above 2, then you need to inject 6. This is important to keep compliance. And sometimes you go to the monograph and you won't find at all like a system suitability requirement to check system repeatability or system precision, right? And what you have in 621 is an approach which can be used in case you judge necessary to include a system precision, which is usually good. So if in case you have an assay procedure for an API or an excipient, and you have the target value is around 100%, and the system repeatability is not specified in the monograph, you can go to 621 and then calculate a maximum permitted relative standard deviation, okay? And I will show you on the next slide how you can do this. So you're going to find in 621 this equation, and again, this is not new, okay? Let's assume you have an assay procedure, and the specification is like for the API is 98 to 102, okay, and the target value will be around 100. And then for you to calculate your B, you just need to do this is going to be the upper limit. In our case, 102. In the case that I shared before. And the individual and the minus 100%. So you take the target values, actually the upper specification limit minus the target value, which is 100, and then you find. Let's say if this is 102, so you're going to get a B of 2. Hopefully, it wasn't so unclear. And then we can select the number of injections we wish to inject the sample, and this is going to be the maximum or RSD you can include as part of your system suitability, okay? Okay, let's go now to the new requirement. This is a system sensitivity. This is the first one. So what is here in these bullet points is exactly the sentence you have in 621 today. The signal-to-noise ratio is used to define the system sensitivity. Okay, that's fine. Everyone knows about that. But what about that? The limit of quantification is equal to or less than the reporting threshold. This is telling you that if you go to a monograph and there is no sensitivity check as part of the system suitability requirement, 621 will supersede the monograph, and you still need to check the system sensitivity if you're working with impurities test, related compounds test, because it might not make there is no reason why we check sensitivity. Maybe there is no reason why for checking sensitivity for assay, right? But you not find this clarification in 621 today. And this is the reason why USP is planning also a revision of 621 to include some clarifications. But we understand why we should include the system sensitivity, right? And the last one is the peak symmetry. It's saying the same, it's saying the following. Unless otherwise stated in a monograph, in a test or assay, the symmetry factor of the peak used for quantification should be within this value, 0.8 to 1.8. Okay. And again, in case you go to the monograph, there is no system suitability requirement to check peak symmetry for the peaks used to quantify. So you need to still comply and run that experiment. So run acquire some data to show this, okay, to show that you are complying, you are fulfilling the system suitability requirements. Hope this is clear. And probably you might be a bit like scared right now, huh? But as I mentioned before, so this specific section on system suitability, it was delayed, okay? It's still not official, so it means we still have some time to December of this year to do some risk assessment and, check all this, okay? And then to finalize my talk, I just would like to list some of the chromatographic tools we provide. First is the chromatographic columns database, where you find actually the classification of columns, if this is L1, L11, and so on. We also have the G phases. This is for gas chromatography, and S will be the different supports. Chromatographic database, I showed you one, when you scroll down the monograph and you have like chromatographic procedures, you find, the database, you can click there and find the column used during the validation of the procedure, which is a very important information for you to support the request of changes in the LC column, right? And then columns equivalency tool is that tool I showed you that you can include the reference column and then find columns with similar selectivity and may really assist here in the, the proposal for replacing a column. Well, with that, this is everything I wanted to share with you. Thank you so much for joining, and I'll be more than glad to answer any follow-up question that you may have. Back to you, Isabel.
Thank you so much. Thank you so much, Amanda, for this excellent presentation. I just wish you were my analytical chemistry teacher when I was in college. I felt like I would have been learning so much more. Thank you so much. We have a lot of questions that were asked. So the first one, and I will push it to the screen. All right. Okay, you should be able to see it. I thought it was a very interesting one here. Okay, so the first question is about the scope of USP 621. Is it only small molecule, or would this also apply to biologics?
Yeah, this is not just applied to small molecules. So you're going to see some monographs we have for biologics where you use chromatographic procedures that we will also be calling 621. This was easy and short.
Excellent. Okay, so we have several questions about system suitability and validation. So let me ask the first one. What is the expectation from the USP if the method was validated using an old USP system suitability requirements, and now system suitability is not passing using current USP requirements?
First thing, we have the 621 allowable changes, right? So when a system suitability is not passing, and we can go ahead, do the risk assessment and propose some changes that will be within the allowable changes of 621. And I believe any observation can be also shared with USP. So we are going to be happy to get your feedback in case you are facing some, issues when applying all those new requirements.
I lost you, Amanda.
Oh, can you hear me? Can you hear me now? I can hear you. Hey. Hi, Isabel. Actually,
I don't hear Amanda anymore.
I can hear you. So I can hear you well. Can you hear me? Can you hear me?
Oh, okay. All right, fine. We have perfect.
Can you hear me though?
Thank you. So I guess I will. Okay, I can't hear anymore. I'm going to move on to the next question.
Can you hear me, Isabel? I'm not quite sure if.
Oh, it looks like the problem is on my end. Unfortunately.
Okay, but this was a good one, so I will try again.
I'm going to turn off my camera.
Okay, I'll do the same here then. This is a good one, so if I can just repeat my answer. Actually, in case you face issues,
and I will ask
right?
Giovanna to ask the next question.
And Giovanna, let me know here in the chat if you cannot hear me, because I can see you are replying to me here. So answering again this question, just in case you couldn't hear. In case you face some issues in terms of passing the system suitability, right? So you can go ahead and do the try to implement the allowable changes of 621. This is the first thing. Yeah, so now I believe we can go to the next one, Giovanna. Okay, so maybe I can just drive that. I don't know. I believe we lost Isabel. So let me see. So there is one here that I would like to emphasize. Requirements for two new system suitability parameters were included in 621, as I mentioned. If a monograph does not have a sensitivity criterion, is sensitivity still required to be evaluated as part of this system suitability evaluation? So actually, the answer is yes. As I mentioned, 621 will supersede the monographs for this specific part, even if the monograph doesn't have one of that requirements for sensitivity check and peak asymmetry, right? So we may still need to go and implement that as per 621. But remember, sensitivity check will be probably, it will make sense that we do this for related compounds procedures, right? Organic impurities procedures, or for impurity procedures. We may not need to do this for an assay. So this is not the intention of 621. Okay. Okay. So Isabel, are you there? Okay, she will log out and log in again. Okay, so let's say. Okay, so there is a question here from Kiran. The peak symmetry limit of 0.8 to 1.8 is only for monographs methods. 621 is applied to Farmacopea procedures. Yeah, so we expect that this will be like a requirement for Farmacopea procedures. But, this is really like up to the users in terms of implementing this as a way to push for quality, right? Because what is behind this is exactly that today we can work with LC columns technology, LC systems technology that allow us to really have thinner picks, right? And basically this is coming exactly to say, hey, today we can start pushing the quality and work with better performance procedures. And we can even have this as a criteria for procedure development, let's say, instead of doing this retrospectively.
All right, I'm sorry about the technical difficulty. I guess that happens. I'm so sorry about that. So it looks like you answered the question about the signal-to-noise multiplier.
I still didn't. I picked another one.
Oh, okay. Okay, great. So if this is okay with you, maybe we can let you answer this question about the multiplier for the signal-to-noise. The question is appearing on the screen. There has been some back and forth about the multiplier. And the question is, should we use 5 times or 20 times the peak width?
5 times. 5 times. So as the old approach. So we tried to change to 20 times, okay, but we went back, and this is also reflected in all other pharmacopoeias as well, European and Japanese pharmacopoeia.
Thank you so much. Excellent. So we now have a question about moving from HPLC to UPLC. And the question is showing on the screen. Does the allowable changes described in USP 621 allow the migration from HPLC to UHPLC? And I believe you addressed that in your presentation, but maybe you want to further elaborate?
Yeah, exactly. Yes. So the short answer is yes. So we can, migrate from HPLC to UHPLC because now we have some allowable changes for elution, for isocratic elution and gradient elution, where we can change the columns I mentioned. And then this will provide us the chance to migrate from an HPLC column to a UHPLC column or platform. Right? We just need to take into consideration all that tricky points that I mentioned, right? Especially regarding like selectivity of columns. But if we are following 621, we are fine to do this migration. Yep.
Okay, excellent. Thank you. And may I ask which question you answered while I was away?
I answered one about the peak symmetry.
Oh, okay.
Actually,
okay.
It was just one.
Okay, very good. So we do have another question about the sensitivity criteria. So maybe I'll ask you this one now. Okay, it's a little bit of a lengthy question. So requirements for 2 new system suitability parameters, sensitivity and pigtailing, were included in the USP 621. What if the monograph does not have a sensitivity criterion?
Okay, Isabel, I lied to you. I also answered that one when you were offline. I'm sorry.
Not a problem. Not a problem. I can move on to another one. We had a question about dwell volume that I thought was interesting as well. This is a question that we have heard multiple times. So the question is, how do we find out the dwell volume for a pharmacopoeial method?
This is a great point. So we have in 621, we have in 621 chapter that some monographs may bring this information, but some of them you won't find. And this is a challenge. And we say that whenever you have this information in the monograph, you can use that to, calculate the increment that you need to add or delete from the initial hold time. But actually, the only way is to find this in the monograph. There is no other way you can find this information.
Okay, very good. Next question about plate number. Is this a relevant system suitability criteria?
This will totally depend on your situation, I believe. Let's say you are working with a column where you are really struggling to have good efficiency, right? And then in order to make sure when you replace a column or you are transferring the procedure, you wish to include that as a system suitability requirement might be interesting, okay? Especially if this can impact like sensitivity of your analysis and so on. It might be that you are working with a procedure where you already have a very good performance, and so you're you're really far away from like the at least 2,000 plate numbers, right? And then you may not need to include a system suitability. This is really a decision you need to take when you are developing the procedure.
Thank you, Amanda. I just saw an interesting question about, I think it's related to the applicability of 621. The question will show on the slide very soon. The question is about chromatographic modalities like size exclusion, normal phase, etc. The question is the system suitability applicable for all chromatographic modalities?
Yeah, so when you go to the monographs, right, and you find a procedure, usually the procedure will be calling 621. And if it's calling 621, this will be applicable. Okay.
Great. We have another question about system suitability, maybe a clarification that you can bring.
Oh, Isabel, just a second. If you can go back to the other question, I believe I got it wrong.
Okay, sure.
I'm sorry, because actually the 621 is superseding the monographs, let's say, I mean, the system suitability requirements, the new ones, right? So if for any kind of modalities, yeah, so the 621 would be applicable. I believe I changed it, you know, the intention of the question when I read.
Okay, but that's it's very helpful. Thank you. Okay, I have another question here that I think might need clarification. It's about the dual correction and how does it impact system suitability. So it seems like maybe you want to clarify this.
So I believe the question is how dual volume may impact performance, right? System suitability, let's say. So I showed you that when we are transferring a procedure from system 1 to 2, and they have different dwell volumes, right? You see that the gradient will change in a different time, let's say, if you do not apply the correction. This is, you know, the reason why for the most of the monographs where we work with gradient elution, we include like initial hold, and this is also a strategy for method development, right? We include like initial hold and make sure the factors, so the way we are designing the procedure, if you change the dwell volume, right, these may also not impact on performance, even without the correction. But in case we know the dwell volume of, system 1 and 2, we can apply the correction to make sure we will not have like impact on sensitivity. Like, let's say for the early eluting compounds, and you do not do this change, and the procedure is sensitive for the dwell volume differences, right? So you may not like be able to detect properly the early eluting compounds, is an example. Or you can have like resolution or the elution order of some compounds changing selectivity. The point is right now, it's not possible for us to know which of the procedures they are robust for the differences in dwell volume. What we try to advocate is during procedure design, we need to do, an assessment of this factor as well. Okay. I don't know if it was clear.
I think it was very clear. Okay, next question. Are there any updates for limit of detection or limit of quantification calculations resulting from updates to USP 621?
No, actually, 621 doesn't bring any approach to calculate the limit of detection. So usually we have this in the chapter 1225 and the chapter, I believe, 1210. Where we have more information about how to approach and calculate the LOD and the LOQ. And this is pretty much aligned with IC 8Q2 revision 1, the current version, where we have different approaches that we can use to calculate that. But 621 is not bringing like how to calculate them.
Great. So one question about monograph methods versus in-house validated methods. The peak symmetry limit of 0.8 to 1.8, is it only for monograph methods?
Yeah, so I also, actually, this was the one I answered while you were off. But if you want to know the answer, I can repeat.
Okay, I think there is a question for me, actually.
Oh.
Yeah. There is a question here about Empower. So let me put it here. The question is, you can see it, you will see it very soon. The question is, are these calculations, I guess the revised calculation taken care of in Waters Empower 3 software? So current versions of Empower allow the determination of the new calculations. And in addition, in future versions of Empower, so Empower 3.8, which was just launched recently, there are further changes to, there are changes to even further comply. So yes, whether you have the latest version of Empower or previous version of Empower, you can determine those calculations. And I actually am looking at the time, and I'm afraid this is all we have time for. So I think we will need to wrap up here. Amanda, thank you so much for this excellent presentation and for the lively Q&A. And I would like to thank the audience as well for the participation and for all the great questions. I'm terribly sorry about the technical challenges I experienced, and I'm glad that everything kept on moving in my absence. We have our next webinar in this series in 2 weeks on August 16th. Lise Gauthier will discuss improving method transfer outcomes using intuitive innovation. So if method transfer is something that is top of mind for you, make sure to log in 2 weeks on August 16th. I also would like to remind everyone that it would be great if you could complete the survey before you leave. And with this, I would like to thank Amanda again and thank the audience again. And I wish all of you a fantastic day.
Thank you. It was a pleasure. Bye.